Alright guys, so we'll be learning the first two units briefly. Okay, for the first 27 slides I would urge you guys to look at Srijai's one. uh, I'll just quickly go through this. Like a computer does processing, it has several units like input unit, output unit, processing unit. It definitely has memory to store stuff. It definitely has a processor to do stuff, which has in turn arithmetic logic unit to do the operations and control unit to coordinate the operations. And it has buses to travel between different kinds of buses. Yes. So we have different functions, and what are all the functions of each unit is described briefly here. Data are the operands in which your instructions operate upon. It could be numbers or it could be encoded characters, right? That you want to process, right? So it operates on memory, processor, and all that. We very well know it. ALU, CU. CU being the control unit is for coordination. Instructions control what to do. Control unit controls when to do. Okay. So that is it. We'll be looking at how to interpret instructions in a while. Bus structure, you have data bus, control bus, and address bus. And buses can be single bus or multi-bus or two bus. Yes. So we are here. So address bus is nothing but bus in necessarily is nothing but a group of wires, right? It address bus carries address information bits. Yes. If I have something stored in a certain memory location that is given an address, then I have to tell that go go to this location and fetch it. So that location should also be carried. So that is why you have an address bus, and you have to fetch the address data from that address as well, right? So data is also there, and control bus is for control signals, right? Beautiful. So you should definitely know. You should take a look at the arrow marks as well, right? You will not have an arrow mark from each of the units to the processor. It will always be processor to the units for the address bus. For the address bus. For the data bus, it could be a bi-directional movement, right? So you can have it from the processor to the output unit or from the output unit to the processor. Yes. An input unit gives to the processor. Yes. And control bus is for overall coordination. You very well know that. And memory could also be there associated together for fetching stuff and putting into the processor, right? And all that is there. So memory consists of many millions of storage cells, each of which can store one bit. Essentially, what is my primary aim? I want to do some process. If I want to do some process manually, I cannot just chumma do it. I want to first store them. I have to fetch signals. I have to decode them. I have to execute them properly, and then I have to put the last writing signal as well, right? Depending on the type of instruction. So in that case, there's a need for me to have a set of memory locations for storing my data, right? So each cell stores one bit. So data is usually accessed in a group of cells that you call group of bits, right? So that is called the word length, right? Word is a group of bits. The memory of a computer can be schematically represented as a collection of words as shown here. So you have a collection of bits that makes a word. So first word, second word, ith word, last word. So collection of words become main memory, right? Main memory is the second major subsystem in a computer. It consists of collection of storage location, each with unique identifier. Definitely, I told you, right? The motivation behind having an address is I want to point out to that location to fetch my data. How will I distinguish it from other guys? So I need a unique identifier, so I have an address. Data is transferred to and from the memory in group of bits called words. That is what we have seen. It can be group of 8 bits, 16 bits, 32 bits. There are different architectures also. Okay. So if the word is 8 bits, it is referred to as bytes, right? The byte word is so common in computer science that sometimes a 16-bit word is referred to as 2 bytes, definitely, right? And 32-bit is referred to as 4 bytes. Yes. So you can store data in memory. This could be data, and you can have addresses. These are all addresses. Addresses is represented in binary, unsigned binary integers. Okay. So these are all binary. You can very well see that. Yes. So to access a word in memory requires an identifier. Although programmers use a name to identify, at the hardware level, you definitely need to put it in binary. The total number of uniquely identified locations is called address space. Address space is the total number of addresses available in that architecture. Okay. So you put that thing as the address space, right? If you have a k bits, the address space will contain 2 per k locations. Okay. So in this case, you see a memory with 64 kilobits. I want you all to understand the prefixes very carefully. Important. Kilo means 2 power 10. Okay. Mega means 2 power 20. Tera means 2 power 30. Giga means 2 power 30, and tera means 2 power 40. Okay. And 64 is 2 power 6, right? So total of 2 power 16 we have. 2 power 16 we have, right? So 2 power 16 means what? To 65536. So the address space ranges from 0 to 65536. 65535, so that total of 65536 locations are available in the address space. And definitely if it has 2 power 16, it will have 16 address lines, right? And given that the word size is 1 byte, right? Super. Now let's understand all these things you know very well. Let's understand. You have memory that holds both instructions and data. It has k address bits, n bits per location address. N can be n, the number of bits per location address could be different based on the architecture type and all that. Yeah. So in this case, if k is 2, the number of locations is 2 power 10, which is 1024, which is 1000, equated to 1000. Similarly, this is equated to 64,000, and so on. 2 power 16, right? And so on. Just few things. Let's understand some problems also. A computer has 32 megabytes. How many bits are needed to address any single byte? Very simple. To address any single byte, what is that 32 megabytes actually? 32 megabytes is 32 is 2 power 5, mega is 2 power 20. So in that case, 2 power 20 into 5 to 2 power 5 will be 2 power 25. So 2 power 25 bytes are there, right? If 2 power 25 bytes are there, then how many bits are required to put one byte? Very simple, log to the base 2, right? So the answer would be 25 bits. 25 bits to address each byte. That is what we saw there also, the logic, right? How many ever locations are there, log to the base 2 should give you the number of bits to address that. Yes. Basic digital design, even we learned that concept. A computer has 128 megabytes of memory. Each word in this computer is 8 bytes. How many bits are needed to address any single word? So now they're asking how many bits for addressing any single word. Okay. Each word contains 8 bytes now. Okay. So in that case, if it is 8 bytes, so let's try to decode this. Total memory space is 2 power 7 into 2 power 20, 2 power 27, right? And each word is what? 8 bytes. 8 is 2 power 3, right? So 2 power 27 divided by 2 power 3 gives you 2 power 24. So literally you can give what? 2 power 24 uh, uh, to uh, to have notations for that word, right? So in that case, how do you represent each word? How do you 2 power 27 words are there? How many represent you each word, right? So in that case, I mean 2 power 24, sorry. So 24 bits would be there to address each word. Okay. So the memory address space 128 megabytes, which means 2 power 27. Each word is 2 power 3. So we have 2 power 24 words, right? Log to the base 2 will give you the number of bits to address that. Very simple. Okay. Done. Two basic operations required in memory are load operation, store operation, right? Load is taking things from the memory, right? Read or fetch, right? Contents of specified memory locations are read by the processor. Store is data from the processor stored in a specified memory location. Processor will tell me, okay, this is maybe after some process or something, it will give you the final data that you go put it in a specified memory location. And there are two ways of assigning byte addresses, right? You can follow either of them. Many systems follow different architectures. It could be Little Indian system or Big Indian system. Okay. How I remember this is Little Indian stands for LLL. Little Indian, least significant byte, is stored in the lowest story address. The lowest address is LSB stored in lowest address in least Indian Little Indian system. That's it. Okay. So we'll take an example. Okay. But essentially LLL, the LSB is stored in lowest address in Little Indian system, and the opposite for Big Indian system. Okay. So let's understand this. What do you have here? You have 46, 78, 96, 54, right? So in this case, how will you store these data, right? The least significant bit should be stored in the lowest address, right? So if the least significant bit is 54, then it will be stored in the lowest address. Lowest address is 8000 here. Okay. In the Little Indian system. In the Big Indian system, the highest bit, right? High significant bit 46 will be stored in the lowest address. In that case, that will be called as Big Indian. All that you know already. Okay. Just the understanding part of it. Basic function of computer is to execute something. It consists of list of instructions to execute it. Basic understanding of an instruction: add a r0 comma location a. It will first go check location a. It will fetch things from the location a, and it will add it with the things in the register r0, and it will store it in the r0 itself. And location of a will not be modified. R0 will be overwritten. That's it. Okay. Again, what to write, where to write? If I say add of let's say r1 comma r2, is it going to add r1 plus r2 is equal to r1, or is it going to do r1 plus r2 is equal to r2? Okay, what is it going to do? That depends on the type as well. Okay, generally it should be specified in the question. For us, it was specified. If it is not specified, you assume something yourself and then write it forward. Yes. Beautiful. So what is load? The same thing, just load operation will take place. It will take the things from the location, LOC. Okay. A control signal will be established, and then R2 it will go and sit. That's it. Okay. Done. Similarly, in this case also, here R2 and R3 contents are fetched and added and put into R4. Okay. And R4 is overwritten. And the order again depends on how they specified in the question. Store of R4 will just store whatever was R4 into the location. Yes, again, order. So for load and store instructions, transfers between the memory and the processor are initiated by sending the address of the desired memory location to the memory unit and asserting the appropriate control signals. I told you, right? So for getting something, you need to first send the address of that location so that I can access what is there, right? And then I can do this further procedure based on what instruction I'm having. Okay. Are we all on the same page? Can I have a reaction from all your side? Guys, a reaction, please. Thank you. Thank you. All right. So this is very, very important, very crucial. Okay. You can expect a question from this region. Okay. So what happens here? This is the general processor architecture. Okay. So this is a processor. This is a complete processor. What happens inside? We have only learned about ALU and CU in our since our childhood, right? ALU does some processing, arithmetic and logical operations. It does. Control unit coordinates. That's all we know, right? And we had memory. We had input output separately. There could be cases when you combine stuff also and all that. We are not going into that architecture. Okay, this is the basic architecture we are looking at. That now what happens here? You have to remember all these terms: MAR, MDR, PC, IR, and general purpose registers. Okay, so what happens in each case? Okay, so MAR stands for memory address register. It stores the addresses. It stores the addresses of whom? Addresses of the instructions. Addresses of the instructions. So MAR holds the addresses. Then what does MDR do? Obviously data, right? MDR, memory data register. Okay, it stores the data specified in that instruction. Beautiful. Then what is stored in PC? PC points to the next instruction in the queue. Okay, next instruction in the queue. Yes. What is IR? IR is going to be the instruction register. It is for decoding and having the current instruction. It has the current instruction in place. Okay. MAR PC contains the address of the next instruction. IR contains the current instruction itself. Okay. So obviously you can observe that from PC it goes to IR, and that is how the loop should be. We will see how the entire process looks like, and you must know that. Okay, very important. And general purpose registers are for intermediate data, right? Intermediate data are put into these registers and they are worked upon. Yes. And you have your control unit that sends control signals, right? You will have your ALU that sends that does the processes. Again, you can notice the direction of the arrows. Addresses are given from the processor, right? Data is shared between the processor and memory input output. Control unit is shared between all of them, right? Memory always gives it to the bus whenever needed, and input output gives it whenever it is needed. Yes, done. So let's just quickly browse through this. Registers are fast standalone storage locations that hold data temporarily. Yes, they are volatile locations, right? Multiple registers are needed to facilitate the operation of the CPU. These registers, specific registers, have different purposes, and we saw memory address register that and which handles the data transfer between Okay, all these is MAR and MDR handle the data transfer between main memory and the processor. Essentially, the data is MDR. The address thing is MAR. Yes, beautiful. Instruction register is just holding the instructions that is currently being executed. Program counter points to the next instruction that is to be fetched from the memory. And instructions are stored in the memory. Remember, even when you worked in the lab also, remember when you clicked in 8086, when you decoded every instruction is given a memory address. Yes, you are putting that instruction into memory, and each time you process it, you will fetch that from the memory and you take it to PC, and from PC it goes from so on to so on and so forth. Okay, we'll see that. So done. uh, General purpose registers are for intermediate results of operation holding data. They're also known as scratch pad. Scratch pad, right? You write it something, scratch it, and so on. Yes. Okay. So this is a nice diagram, actually. Okay. So same diagram with all the important stuff not properly given. So firstly, the program gets into the, so whenever asked about the processor architecture or these units, make sure to draw these diagrams, very important, right? So program gets into the memory through an input device. Yes. So firstly, you are putting, take 8086 for example, you are writing the instruction in a certain memory, right? So program gets into the memory through an input device. Beautiful. Execution of program starts by setting the program counter to point to the first instruction of the program. What do you do when you want to execute the program? You click enter every time, right? Firstly, it points to your program counter. Okay, the program counter points to the first instruction, right? Next, the contents of the program counter are transferred to whom? MAR, the addresses, right? So the contents of PC are transferred to the MAR, and a read control signal is read to the memory, right? Because I have the address, right? And I have to read what is there in that address, that instruction. So I have to initiate a control signal, read control signal to the memory. Memory, the instruction is stored. The addressed word here, it is the first instruction of the program, is read out of memory and loaded into MDR. So what you do? Take the instruction out. Okay, these are all the things loaded to MDR beautifully. And the contents of MDR are transferred to IR for instruction decoding, right? So what happens here? Now I have to decode the instructions and execute it. So IR will have the current instruction in execution. Yes. The operation field of the instruction IR is examined to determine the type of operation. Now what happens? I have my current instruction now in IR, right? Now what will I do? I have to send it to somewhere in such a way that the instruction will get executed. Where will I send it? Somewhere it gets processed. A arithmetical logic unit, right? What operation should I do? I should determine it. So the operation field of that instruction will tell me what type of operation to be done. The specified instruction is performed by obtaining the operands from the memory locations or from the general purpose registers. So so you get it from the memory locations or general purpose registers. You know the operation it is. You perform it in ALU and you do the remaining stuff. That is writing it back to the memory or something like that, and or giving it as output. So fetching the operations from the memory requires sending the memory location address to the MAR. Now I want to fetch the operands, right? I just had only the memory data now. Get the operands first. How do you get the operands? You know the address. Address will be specified in the memory, right? So you will send the memory location address to your MAR. That will initiate a read cycle. It will go to the memory. It will give that data, that operands data into the MDR. MDR to ALU. ALU will do the operation, and it will send the result either to the memory location or the general purpose register. The result is sent to MDR, and the address of the location where the result to be stored is sent to MAR and write signal. So you now have to send the data. So after things are done, it will send to MDR first, right? And then I have to go write in the memory of DNA. What do? I have to I have to tell which address I have to write. That is also specified in the instruction, right? So I'll send that address also, right? So in that address, this specific data is written and write cycle is initiated. That's it. Okay. So start load address to the program counter first, and then goes to MAR and all that, and instruction register updates program counter to the next instruction. You execute it and keep looping over unless you have an interrupt. If you have an interrupt, it is a high priority signal. You have to go fetch service that interrupt using interrupt service routine, ISR. You'll have an interrupt vector that points to the start of the interrupt service routine. That will get serviced, and you will come back to the same program where you were already. right? Until then, you will store all the contents that you were having till now somewhere else, and after that, that wherever you stored it, you will fetch that back and do it. Okay. Okay, they have given it. Yeah, done. Now, instruction and instruction sequencing. Instruction is the command set of operations, right? Is a command to the microprocessor to perform a given task on a specific data. Instruction set is just the group of these instructions. Instruction sequencing is the order in which you execute these instructions. A computer may have instructions capable of performing 4 types of operations, right? They can do what? Data transfer between memory and processor. They can do ALU. They can do control operations. Sequencing operations are nothing but branch operations. They can like go, let's say they are doing first, second, third, fourth, fifth. The fifth thing should say jump back to second, something like that. That is also available. Yes, and input output transfer is also there. Okay, beautiful. So transfer between processor registers and memory. So register transfer notation is basically telling us the transfer between how register length memory or register length register, right? How does it work? And input output devices. How does the transfer work, right? So memory locations, registers, and input output registers names are identified by a symbolic name and uppercase alphabets. Just you can note this down. Okay, these are all just simple memory location addresses. Can someone confirm if you guys have assembly language code for in semester? I suppose you should. Can one of you open your mic and tell me? Unmute.
Can you repeat?
Do you have assembly language code?
I don't think so. You're selling cyber doesn't have codes, nala mostly you won't ask.
Okay, done. So
But all of the addressing modes are there, but writing code is not there.
but he generally says when he keeps code. Okay, he didn't say va. Okay. So these are all just specific notation. Just note R not are just processes registers. Data in, data out are just input output registers from which you can fetch the input and output and give back output. Contents of location is indicated by square brackets, important, right? So when you have a location, to specify what is under that location, you just have to put square brackets. That will tell me what data I'm putting. Again, 8086. Remember when we were giving input to the 8086 machine, we were literally going to some random location that we specified in our instruction, and we are giving our input. We are putting our input there, and we are leaving it there. And when we execute the program, automatically what happens? Your data is fetched from that specific location. Yes. So the contents of that location is specified by this square bracket. RHS of the register transfer notation always denotes values and is called source. LHS of the register transfer notation always denotes a symbolic name where value is to be stored and is called destination. Yes. So in this case, RTN, RHS is source, LHS is called destination. Source contents are not modified, but destination contents are overwritten. Okay, ma? Simple ones, right? See this location. From the location, it goes copies to R2. From adds the content of R3, adds the content of R2, fetches, adds, and gives it to R4. Yes, and overwritten. Data transfer instructions are called copy instructions. What do you do? Some instructions are 8086. These depends on the architecture. Yes. So move is going to copy from source to destination. Load is going to load it to the accumulator. That's it. Just load it from the accumulator. The accumulator is very useful in context where you don't have any specific second address, right? In that case, what can you do? You can always use the accumulator as a buffer kind of thing, and you can do your operations. And store will just store in the accumulator. When you don't specify anything, it will just store it in the accumulator. Yes. Push will just push it onto the stack. Pop will pop off the stack. Okay. Now, data manipulation instructions are stuff that processes, right? The arithmetic instructions, logical instructions, shift instructions are all the data manipulation instructions. You can do an arithmetic instructions, for example, just incrementing, add 1 to it, decrementing, add decrease 1 to it. Again, increasing by how much amount, decreasing by how much amount depends. Okay, depends on the word length, depending on the word length. Okay, add just perform sum. ADC is add with the consideration of carry, add with carry bit, and just as multiplication. Okay, and logical operations like and, or, not, XOR, we very well know that, right? These are all bitwise operators. Shift instructions, shift right. Okay, rotate bits towards the left, right? Rotate bits towards the uh, with the consideration of carry, I guess, right? MSB to carry flag and carry flag to LSB. Just know these instructions, not so much. This will not be that important, but know it. That's it. Instruction formats is the types of instruction based on the address fields. An instruction in a computer comprises of groups called fields. Each field contains different information. You should have seen the 8086 layer. Okay, opcode we saw something. We have different fields that specifies different information. Okay, so operation field specifies what operation to be performed. Okay, address field contains the location of the operand. Mode field specifies how to find the operand itself. Okay, so based on the number of addresses and instructions can be different types: zero address, one address, two address, three address. Okay, zero address instructions do not have any locations or addresses specified explicitly. They're all implicit. Okay, so operands are stored in a structure called push down stack. You make use of stack. So let's say we want to evaluate this a plus b star c plus d. How do you do it? First, you have to take the data of a. So you do push a. If you do push a, then the top of stack will have a. Then you do what? Push b. When you do push b, the top of stack will have b now, right? Beautiful. So now you will have a in the bottom and b in the top. When you do add, what happens? B and a get added. Then where will it get stored? The top of the stack. Yes. Now the top of stack will contain a plus b now. A plus b. Yes. Now a plus b contains. Now you push c again, and then you push d again. Again you give add signal. Again the things which are below c and d, below that top of the stack thing will get added up, right? In this case it was just c and d. Yes. So c and d will get added up. Now the top of stack will get c plus d. So we had c plus d. Now all these guys will be popped off. Okay. So c plus d you have c plus d into c plus d you have, and you had a plus b already in the bottom. Now you just give mul c plus d, bottom layer we have a plus b. Now you give mul, both of them will get multiplied, right? Eventually the whatever operation you are giving, the top of the stack and the one which is below top of stack will be operated, and the top of stack will be the result of these two operands, right? Based on the operation. So now it will contain a plus b to c plus d. And now you are giving pop of x. Now when you give pop of x, that will just do what? Copy the value from the top of stack to this particular memory location. Okay, beautiful. One address instruction is used when you have no second instruction, right? Only one instruction is present, and you will make the reference of accumulator in this case. Okay, so in this type, either a source of destination operator is mentioned, other operand is implied to be what? The accumulator. Okay, so what happens here? Let's say we want to do the same a plus b into c plus d using one address instruction. So in that case, what I'll do is first I load a. If I load a, accumulator will contain a, right? Accumulator will contain a. Now I have to add b, right? I cannot just load b. If I load b, now accumulator will just contain b, right? This is not stack to store a lot of things, right? So I will not instead do load b. Instead I'll say add b. If I add b, then what will happen? It will add a, the current contents of the accumulator with b and store it in the accumulator itself, right? So in the case, the accumulator will now contain a plus b, right? Now I have to modify accumulator for c plus d operation. So now I'll store it. So I'll store it at a location, let's say store t, right? One address only I can specify. So store t, I'll store it. Beautiful. Let's do the same thing again, right? Let's load c and add d. Now accumulator will contain c plus d, right? Now accumulator contains c plus d. I need not store it again. Accumulator itself contains c plus d, and the memory location t contains a plus b. Now if I just say what? If I just say multi, if I say multi, so if multi means what? Multiply whatever is in the accumulator by t and store it in the accumulator itself. Now accumulator contains c plus d. The memory location contains a plus b. A plus b times c plus d will be stored in the accumulator now. And finally, you do store x, and that will do what? Copy the accumulator contents to the memory location x. That's it. Okay. Are we all clear till this point? Can I have a reaction from all your side? Thank you. Thank you. Now, to address instruction. What happens here? You will have two operands, and you will do what? You will copy. The destination could be either of the operands, and you will never know which is the one that should be specified in the question I told you. Yes, beautiful. Perform addition of ABC using two instructions. How will you do it? Move B comma C, okay, and add A comma C. What happens? You are first of all moving B to a memory location C, right? And then you are adding whatever was in C, you are adding it to what? A, and then you are storing back to C again. So in turn, C will contain A plus B. That is what we mean. Or um, if they imply addition of A, B, C, it should be different. If they are implying only addition of A, B and store it in C, it should be just moving the thing and then adding up. Yes. So let's try to understand this example with this, right? Now to address instruction for this. How will that look like? Firstly, you have to add A plus B, C plus D, multiply. That is the order of the instruction. Okay. So what do? You will first of all, so here they are using, they are making the use of registers. Yes. So they are trying to move the contents of A to a register R1 easily, right? Contents of A to R1. Okay. Then whatever was in R1, they are trying to add it to the contents of B. So in that case, how will you write the instruction? Add R1 comma B, meaning what? Whatever was in B, add it to R1 and store it in R1, right? Super. Now you have R1 containing what? A plus B, right? Now what can you do? Let R1 contain that, right? Let R1 contain that. Let's go to the next one, right? So move R2 comma C, right? Now move R2 comma C will store the contents of C to R2. Again add R2 comma D. Now R2 will contain C plus D. Yes, R2 will contain C plus D. Now R1 contains A plus B. R2 contains C plus D. Just mull R1 comma R2 will do my job, right? Yes. Now R1 will contain R1 into R2. Just store R1 at a specific location X. So in the case, moves the thing, right? So move X comma R1 will just move the contents of R1 to X. Okay. Three address instructions, very simple. You'll have two source, one destination. Okay. A single instruction can perform the complete operation. That is advantage, but it will be a very large instruction code. Right? It will be too large to fit in one word location. That's one of the problems. Here, single instruction is not sufficient to put everything. That is another problem. Here, you make use of stacks, accumulators. Good thing only. Okay. Now, instruction cycle, again, very important. You should have learned this very well in your pipelining chapter as well, right? Fetch, decode, execute. Fetch, decode, execute cycle, right? So this process is being repeated continuously by CPU from boot up to shutdown of a computer. Fetch the instruction, decode the instruction, read the effective address, fetch the operands, execute the instruction. Yes. So what happens? Fetch the same thing I told you. They're just repeating it again. The instruction is fetched from memory address that is stored in program counter, and then it is put into MAR and then put into IR, then decoded in the IR, right? And at the end of fetch instruction, PC is incremented by 1 so that it points to the next instruction. Yes, you will read the effective address. If the instruction has an indirect address, the effective address is read from the memory, right? You have this logical physical address conversions, right? Effective address, you might not have all the addresses to be physical address. In turn, you will have a certain offset first of all, and you will have a certain memory, memory address. You will map it according to that. So effective addresses should be also taken care of, right? Otherwise, operands are directly read in case of immediate operand addresses. Fine. Now you execute it. The control unit passes the information in the form of control signals to the function unit of CPU, and then they coordinate with each other. It is stored in the memory or put into output. This cycle is repeated again and again by repeatedly incrementing program counter, then going to instruction register by fetching it, effective address calculation, execution of instruction. Right? Yeah. So operands are fetched from the memory. If there is more than one operand, the operand fetching process may be repeated. The address calculation fetching operation can be repeated if the operands are more than one. Okay. Yeah. And then data operations could be performed and result is generated. If a result has to be stored in a register, instructions end here. If the destination is memory, then again you have to do that. You have to send the destination address, calculate it, send it, result is then stored in the memory. If there are multiple results to be stored, this process may be repeated. Now the current instructions have to be executed side by side. PC is incremented, same stuff. Straight line sequencing is there is no branch instruction. You just go line by line, sequential manner. Okay. The PC is incremented by a fixed offset. So how it happens? Programs and data are stored in the same memory. That is one Neumann architecture. That is, data refers to the variable in a program. One Neumann architecture is they are stored in the same thing. Program and data together. Okay. The first instruction of a program is stored at address I. PC gives address I, and instruction stored at address I is fetched from the memory and executed, decoded, right? Then operand A is fetched from the memory and stored in a temporary register. Instruction is executed and incremented the pointer. Now the pointer would go to depending on the type of data. Right now here in this case, by depending on the word length, they have incremented the pointer by 4, right? Because it is of 4 bytes, right? It contains the address of that 4 bytes tells the next instruction. The instruction contains 4 bits, 4 bytes. Okay, so in that case, that. So the ALU path is supplemented by few registers, which holds the data quite temporarily. That is why you have various registers to accompany this, right? Every time the PC is incremented by this, we very well know that. And straight line sequencing, just this execute, very simple, execute this, execute this, execute this, straight line sequencing. Okay. The addresses of the memory locations containing the n numbers are represented like this. The first number is stored into memory location this, and every other number is added to the registers R0. Finally, when the program ends, the result is stored back to this sum. Basically, you're just storing num1, num2, num all these guys in certain addresses, and sum is stored in the final address after these guys get executed. And you have different way of defining instructions based on the conditional flags. So conditional flags, if the result is negative, the n flag becomes 1. If it is positive, it will be 0. If there is a 0, the 0 flag will become 1. If it is non-zero, it will become 0. Overflow na 1, illana 0. Carry irukna 1, carry illana 0. Okay. So different formats of instruction, you will have an opcode, you will have an operand, right? These operands could be different. These operands could be all 3 registers. It could be just 2 registers. It could be just 1 register, or it could be a memory address register, or it could be a register memory address, or it could be a register and a number also. Okay. So and we'll be seeing these in the addressing modes now. Okay. Addressing modes are nothing but different ways of specifying my operands in my instruction. Okay. Different ways in which location of the operand is specified in an instruction is referred to as addressing modes. The purpose of using addressing mode is to give the programming versatility to the user. Different ways in which I can do nice stuff, right? I get the liberty. Next, to reduce the number of bits in the addressing field. That is also one of the purposes. Okay. There are different ways of addressing modes. You should learn all of them carefully. Very important. Okay. Immediate addressing means I'm putting my data directly. Okay. That is immediate. Okay. Operand is given explicitly in the instruction. For example, add 5. Because I'm not giving any address here, 5 is getting added to whom? Accumulator. Okay. Add 5 to the contents of the accumulator here. Right. 5 is the operand. There is no memory reference to fetch data because there is no address itself. Right. So it is quite fast. It has limited range because you cannot just always do this. So move AL comma 25H. Right. What does this imply? Copy the value 25 to the address AL. That's it. Copy the value 2345 to the address AX. Right. That's it. And you will you will have lower address, higher address, right? Lower part of an address and higher part of an address. In this case, AX might have 2 blocks inside, AH and AL, right? And AH here stores this 23 and AL stores 45, right? So together, AX stores 2345. That is what I mean. Okay. Now, what is direct addressing? Direct addressing is like you will have an instruction like this. There will be an opcode, there will be an operand. Operand here is nothing but a memory location. Operand here is nothing but a memory location. It will just go search for the memory location, take whatever was stored in that memory location, take it back. That memory location will have the value, that data, right? The contents of that memory location will be processed further. Okay. So address field contains the address of the operand. Effective address is nothing but the address field itself, right? In this case, add A will just point out to that address field, which is a memory location. So add contents of the cell A to the accumulator. So here, because I don't have any other address specified, I will reference it with respect to accumulator. So whatever is in accumulator, add it to content A and put it back to accumulator, right? That. So there is a single memory reference to access data, no additional calculations to work out effective address because it is a directly, right? So limited address space. You can check through my paper for finding effective address calculation as well. Okay. Now move AL comma data one. What will that do? Data one directly copy to AL, right? Superb. This is direct addressing because you have a single memory reference here. Okay, don't say because directly data gets stored, it is not immediate addressing. Okay, done. Now data 2 gets stored in AX. Fine. Here data 3 could be stored, data 4 could be stored, and so on. Okay, so again I told you it could be AL and and all that. I told you it is sequentially between the lower blocks and upper blocks. 23 gets that, all that is it. That's it. Okay, so based on what data you are giving, that will be stored in the respective locations. That is all that you know. Okay, indirect addressing is you will not specify the exact location. Instead, you will give a pointer. You'll give a pointer. How do you know it is a pointer? You will put parenthesis. Okay, so if I say add of parenthesis of A, I mean to say, okay, A is not where my data is located. What I'll do is I'll go to A. Okay, A will contain the address that will tell me where the data is located. Okay, so I'll go to the address where the contents of A contains. Okay, and that address will contain the data. So this is essentially a pointer. Okay, so memory cell pointed to by address field contains the address of the pointer to the operand. Operand is what I'm looking for. That is not directly explicit. That only contains the address of that operand. Okay, indirect addressing modes is that is what we have been seeing, right? So A goes to the memory, checks it, it will have something. You go to that is the effective address. You go to that, you see the operand there. Yes, beautifully. Now in this addressing mode, the operand is contained in the register. So what is this? The same thing with the register here. You are seeing just direct, indirect. You can also have register direct, register indirect. In register direct, you fetch it from register directly. Okay. If it is indirect mode of register addressing, then you will have a register that will contain the address of a certain memory location. You will have a register that will have the address of certain memory location. You go to the memory location that will have the correct data operand. Okay, so that here you will have no memory access because you're only using registers. Very fast execution because the registers are the most fast accessing things, and cache is also there. That is even more faster. Okay, so cache coupled to the CPU I'm talking about. Okay, so very limited address space is there, right? Because it is a register, and limited number of registers are only available. Very small address field is needed. Shorter instructions, faster execution. Instruction fetch. In this case, add R will just copy the contents of accumulator with the contents of this register and put it back to accumulator itself. Register indirect is this, right? So the register field of the instruction refers to the CPU register that contains the effective address of the operand, right? So you are not registered in this case memory location in the indirect addressing. We are having a memory location that pointed to another memory location. In this case, we will have a register that will point to a memory location. That is the difference. Okay. So only one reference to the memory is required to fetch the operand. So in this case, add R will increment the value of the value stored in the accumulator by the contents of the memory location specified in the register R. Meaning, I'll first go to register R. Whatever was there in the register R, I'll go check the memory address. Whatever is in the memory address in the memory location, that content I'll copy to AC, add it, and then copy it back to AC. That is what it is. Indexed is by a certain offset. Okay. So what happens? Effective address of the operand is obtained by adding the content of the index register with the address part of the instruction. So what happens? You will have a certain offset in which you will drift back, and that will be the index register. Index register will have something, and the instruction will have the address, right? So that address you will add it to this index register contents, that will be the effective address, and you will go search the content in that effective address. Getting that? So that is index mode of seeing it. Relative is the same index register with the index register being program counter. That's it. Okay. So a version of displacement addressing. Yeah, by the way, that is called displacement addressing. Okay. So a version of displacement addressing in this effective address of the operand, effective address of the operand is obtained by adding the content of the program counter with the address part of the instruction, and you go search for that. Auto increment is a special case of register indirect. So what happens here? Basically, whatever is in the register, that will become the effective address, and is increment by one. That's it. Take it. It's like x plus plus. You copy the value of x. One is required to fetch the operand. Yes. So in this case, it go the 3300. So it will automatically fetch 3300. That is 6B, and then it will get incremented by the amount of bits bytes. Here it gets incremented by 3300. Okay, that's step size. Auto decrement is the same thing with reduction of step size. And you not step size. Then uh, yeah, Deepak, yeah, am I clear now? Hello, hello.
Okay now.
Thank you. Yeah, so that is auto decrement, right? So all these things are not much required. You can just skip these fields. Just know that these fields exist. I'm not going deeper into this. And assembly language are converted to existing machine language. All this is just for your general knowledge. You should know that. After that, you will have a very big code, right? You will have a Python code, high level language that will be transferred to a low level language, and then that becomes an assembly language, and that becomes the machine language, zeros and ones. So they're just showing how it happens. Okay, just know that micro was a microcontroller. I'm just going too much. I'm not going deeper into this. Microprocessor is a CPU on a single chip. Microcontroller in turn contains everything. Microprocessor is just a processor. Okay. Microcontrollers have everything, input, output, memory, and all that together. That becomes a microcontroller. Okay. So microprocessor, you can see this is just the microprocessor, CPU alone. If you put everything together, that becomes a microcontroller, right? 8086 is a microprocessor. Arduino, is a microcontroller. Yes. So this is general purpose. This is single purpose. This is expansive, not expansive. This uh, this can be modified, customized based on your design, right? This is properly designed, and then you use it for a specific application. Okay. I just know this difference. Okay, they can ask you this difference actually. So this CPU standalone here, all these guys are separate. All these guys are together on a single chip, right? The instruction set of a microprocessor is complex. The instruction set of a microcontroller is very simple with less number of instructions. Okay, so block diagram of microprocessor, you'll have an ALU, register section, control timing section. Already we learned all these guys. The same processor architecture repeats in the context of microprocessor. That's it. Okay, same things. You have in RISC architecture and CISC architecture. RISC architecture is reduced instruction set computer. CISC architecture is complex instruction set computer. Okay, so how does microprocess evolve, all that. Just if you want to know, you can know it. Okay, I'm just skipping them. First generation is just doing simple arithmetic operations. They are having a simple control unit. Second generation is the first 8-bit microprocessor that could perform arithmetic logic equation. Here it was 4-bit only. Then second generation became 16-bit, represented by Intel's 8086 and all that we have in our lab. And then fourth generation was 32-bit, and fifth generation was 64-bit. Just know that. That's it. Okay. And 8086 supports two modes. Maximum mode, that is suitable for systems having multiple processes. Minimum mode is just one processor. Okay. Fetch stage, execute stage, and all that, they have explained it. The same thing, microcomputer, a digital computer with one microprocessor which acts as a CPU. That's it. It's just a microprocessor with a computer thing, right? A complete computer on a small scale. That's it. Okay. Designed for use by one person at a time. This is called personal computer, a device based on single chip microprocessor. That's what you call it, right? Laptops, desktops, and all that. And how do you define the performance of a of an instruction of a set of instruction itself, right? So performance of a computer is how quickly it can execute programs, right? Speed with which it can execute programs is nothing but what, determining the performance, how much nicely I do, right? For a bike, the mileage, how much kilometers am I going to travel with this much amount of liters of petrol, right? Or how much liters of petrol is needed for travel this much kilometers, right? Similarly, how much instructions can be executed in this much time, or in this instruction requires how much time to execute, all that is there, right? So you are considering all those factors. So in this case, first of all, how is the hardware? That definitely depends. And how is the machine language instructions, and how is the compiler that translates your high level language to machine level language. All these guys are dependent factors on the performance. Yes, for best performance, your compiler design should be properly coupled, right, with your machine language instructions, right? Properly coupled, as in, I mean to say that they should be compatible, right? In such a way that coordination is required between compiler design and machine instruction set. Processor clock, that is going to give me timing signals when which should execute. Again, these are all coordinated by whom? Control unit. Yes. So they have specific regular intervals. Clock defines specific regular intervals called clock cycles. And in one cycle, I can complete one step. And every instruction is divided into different steps, right? And I'll execute one step of an instruction in one cycle. So if P is equal to the length of one cycle, then what is the clock rate? Clock rate, very well you know it, frequency. You've learned about frequency, right? Frequency is 1 by time, right? How many cycles per second? Similarly here, how many cycles are taken for the length of one for that instruction. So in this case, R is equal to 1 by P. The length of one clock cycle is P. So the rate should be what? 1 by P, right? 1 by P. So that will be in frequency terms, hertz or cycles per second. So just know that R is equal to 1 by P. So in general, the clock rates of today's computers processors have millions to billions clock cycles per second. Okay, beautiful. Now, basic performance equation is T is equal to NS by R. Okay, what is this? N is going to be the actual number of instruction executions, meaning I have N instructions to execute. Okay, then what is S? Number of steps to execute one instruction. I have N instructions. I can execute one instruction, average number of, because not every instruction will have a same number of steps to execute. So let's say average number of basic steps to execute one instruction is yes. And one step can be executed in one clock cycle. So T is equal to N into S, got it, right? We very well know time is equal to distance by speed, remember, right? Here distance is the total number of instructions that I have to cover. Total number of instructions is just total number of instructions multiplied by total number of steps, N into S, done. Divided by R is the speed, right? Clock rate. So T is equal to NS by R. So if you want high performance, I want less T, right? Less time. If you want less time, then I want lesser number of instructions or lesser number of steps to perform one instruction or greater clock rate. That is what they mean. Okay. Pipelining and superscalar execution are very useful in this case because you can execute multiple instructions at the same time by displacing the fetch and decode operations. We saw fetch, decode, execute cycle, right? So when one is fetching, maybe it went to decode state. In that thing, I can fetch the other instructions data, right? So that is pipelining and all that. Superscalar, you have different processes to execute. Multiple function units are there for parallel paths of execution. Okay. So higher degree of concurrency can be achieved if multiple instruction pipelines are implemented. Meaning, I can execute multiple things at the same time by doing this pipelining, right? Now, clock rate again depends on the IC technology. IC is made of logical circuits, right? So that it depends. It definitely depends on the value of P, that is amount of processing done in the one step. So that and risk and risk we will just see quickly. Risk is nothing but simple. You will have simple instructions. CISC is complex instruction. So imagine if you have simple instructions, then the number of instructions will be greater, right? Number of instructions to execute that instruction will be greater. Similarly, if you have complex instructions, the number of instructions will be lesser because you have one instruction large enough data, right? The fewer instructions are needed, but yeah, the number of instructions are greater. That is, S is greater, N is lesser. Here, large number of instructions are needed, so N is greater, but the number of steps will be lesser. That's why it is simple. Okay. Compiler, an optimized compiler would reduce this product NS. NS will tell you the total number of clock cycles that used to execute the program. Right? Compiler has the liberty to arrange the programs in a nice way to execute it in such a way that time can be reduced. High quality compiler must be closely linked to the processor architecture. Obviously compiler translates high level program to machine language instructions. So you have to reduce the total number of clock cycles needed to perform a required programming task. That is your whole objective in making performance criteria. Correct? Now, performance measurement. Performance measurement, I want to compare how well this computer performs. Computer performs, right? Then how will I do that? So to do that, I will try to reference it with respect to another computer. These are all reference scale. It's not absolute for this computer alone. It is with respect to a reference computer. That's it. Okay. We had a problem in this in our I'm not sure if my paper. It was my senior paper, I guess. So the performance measure is the time taken by the computer to execute a given thing. We very well know that. So spec rating stands for System Performance Evaluation Corporation. Spec is that organization that gives me a benchmark, right? So what you'll do is to find the spec rating, you will have your own computer that you want to measure performance for. That is called the test computer. You will have a reference computer with which you will compare. So how much ever time it takes on the reference computer divided by how much time it takes for the test computer is going to give you the spec rating for a specific program, correct? You'll repeat it for all the programs, right? You'll repeat it for all the programs. Okay. So by repeating it for all the programs, the spec rating will come out to be what? Let's say there are n programs that you're executing. Then in this case, it will be spec 1 into spec 2 into spec 3 into spec 4 till spec n whole power 1 by n. That is what they mean. Spec 1 into spec 2 into spec 3 till spec n whole power 1 by n. That's it. Right. So the program selected range from very complex range to very numerically intensive range, blah, blah, blah. Yeah. Instruction set architecture is a part of the process that is visible to the programmer or compiler writer. ISA serves as the boundary between software and hardware. We saw all these architectures and all that, how it works, stack, accumulator, general purpose registers are all available. You know about stacks, accumulators, shorter instructions, and all that we saw. General purpose registers for storing the intermediate values, make code generation easy, and you can be stored for longer periods in registers, a little more. Okay. And you have different set of ISAs. While the CPUs are clearly better than previous stack and accumulator operators, they are still lacking in few areas. Instructions were of varying length from 1 byte to 6 byte. This causes prefetching and pipelining problems, right? When you have a certain stack or accumulation, that is just fixed. But when you have variable length data instructions, that is causing some trouble. ALU instructions could have operands that were memory locations. Yeah, that is also there. So you have to go access the memory every time. The number of cycle it takes to access memory varies for the instruction also, right? That is not very good. Most ALU instructions had only 2 operands, where one of the operands is also the destination. So you are just literally destroying the content of the operand and rewriting it. So you have to save it if you need it again, right? All that. RISC is properly covered, I think, in the 5th unit lecture. I want you to go through that. Okay, I think signed unsigned is also properly covered. Signed numbers for you express a number in binary. For the positive numbers, everything is same. Only for the non-positive numbers, right? Uh, you will do what? You will add these bits, right? It will be different for different kind of sign number test systems. So in the sign magnitude system, you will add a sign bit in the LSB, not the LSB, the leftmost side. Okay, so that will be what? One for a negative case and zero for a positive case. In one's complement, you just take the complement of it, invert all the bits. Zero becomes one becomes zero, right? And the range of one's complement and sign magnitude is same. That is minus of 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. The range of one's complement is the same, minus of 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. Okay, and both of them have this issue of two representation of 0, plus 0 and minus 0. In this case, the plus 0 would be 0 0 0 0, and the minus 0 would be 1 0 0 in sign magnitude. In sign magnitude, there's an error here. There is an error here. Okay, but in one's complement system, plus 0 would be 0 0 0 0, but minus 0 would be 1 1 1 1. Again, two representative of 0 also. So to get some proper interesting stuff here, you're making it consistent. You're having a two complement system that gives you only one representative of 0. That is just uh, 0 0 0 0. How do you do that? By adding 1 to it. 1 1 1 1, add 1 to it, it will become 1 0 0 0 0. Okay, in that, and you will, because it is a 4-bit system, you will only take care of the last 4 bits. So that one is clearly ignored, and you will only have 4 bits. So that is the importance, and you have everything displaced by one position here. Okay, so you, this table is important. Okay, he usually asks this, right? So just know this, right? So sign magnitude, all the positive numbers you see same binary representation, everything is same. Negative numbers, you will have one at the leftmost bit. One's complement is just the complement inverting all the bits. Two's complement is just displaced by one position. This 1111 will come here. Okay, so this 1110 1101 will come here, 1100 will come here, so on, so on, so on, so on, so on. So in that case, you will have an extra representation here. So the range will be nothing but minus 2 power n minus 1. There is no plus 1. There is no plus 1. Okay, minus 2 power n minus 1 to 2 power n minus 1 minus 1. That's it. Okay, floating point IEEE standard. This is also very important. Okay, so how do you do this? We'll quickly see this. I think I'll be better with my own thing. Just give me a second. I'll take my thing. And with that, I think we are done. These instructions you can go through. Okay, logical instructions. Just it is like an appendix section. If you want to understand few instructions, you can always go through this. Just know it. Know how things work. Don't go too complex. Basic instructions should be fine. Yes. So we are just left with floating point arithmetic, and that is IEEE system. We'll quickly see that. Until then, can I have a reaction from your side, guys? Yeah, thank you. Yeah, just quickly, just give me a second. I load it. Uh, can you confirm if the screen is visible? Is the screen visible? Deepak?
தெரியுது.
Okay,
ஆ
thank you.
தெரியுது.
Huh. Okay, so let's quickly complete IEEE system. So you have different precision systems in IEEE. Why do you use IEEE to represent floating point numbers? If there is a simple binary number, I can represent it nicely. When I have floating point, something represented in terms of into 2 power, right? How do I represent it? So that is why you have this nice system. So what happens here? Let's quickly see. Firstly, you will have a certain number given to you. Okay, we will be looking at examples. For now it could be a blind theory, just see it. Okay, you will be given a number. Okay, you will represent that number in this format. Which format? Plus or minus 1 point f into 2 power m. Okay, why 2 power m? Because it's a binary number, base will be 2. Okay, and what is going to be m? M is going to be the exponent. M is going to be the exponent. That is how many bits you shift. Yes. And what is f? F is going to be the significant, right? The floating point value, that is the significant. Okay, the different ways for the names for this, that is up to you. Okay, but just go through that. You will have three fields essentially when you are representing a floating point number: a sign field, exponent field, significant field. Sign field will tell you whether it is a positive number or negative number. Exponent field will tell you what is that 1 point something. And if there is a significant field, that will be just 2 power something. Okay, why 1 point something? Why not 0 point something? I mean, it's not it's very much implicit that whatever is 0 point something, you can convert it to 1 point something. Okay, so I show you how it is done and all that. And whenever you are putting something into exponent field, right, what you will do is you will add a bias. You will add a bias. Why do you add this bias? End of the day, I'm trying to represent everything in an unsigned system. In an unsigned system, I need to convert minus 127 to 128, that range, to 0 to 255 range. 0 to 255 range. So essentially, for every whatever bit number it is allocated for that exponential field, right, according to that precision system, you will add 2 power n minus 1 minus 1. Just remember this formula: 2 power n minus 1 minus 1. In this case, we are for a single precision system. For sign bit, we'll give 1 bit. For exponential, we'll give 8 bits. For significant, we'll give 23 bits. Add it all up, you'll get 32. Single precision system is 32 bit or 4 bytes. Okay, so 1 plus 8 plus 23. Yes, so here exponential field is given 8 bits. So in that case, 2 power 7 minus 1, that is 128 minus 1, that is 127. I'll add 127. Okay, so that is the single precision system. Okay, so all that is there. Now let's try to do this. One sec. Yeah. In these three numbers, which should be the greater number? In these three numbers, which should be the greater number? You have a sign bit 0, sign bit 1, sign bit 0. So sign bit 0 signifies what? Sign bit 0 signifies whether it is positive or negative. Sign bit 0 signifies whether it is positive or negative. Positive, right? Right? So we were using 1 in all the ones complement, two's complement system, sign magnitude system. Everywhere you will see that it was 1. Yes. The same thing we are using here. Sign bit was 1. So this is a negative number. So in that case, first number will be greater than the second number. Now it totally depends on whatever 1 point that f and the exponent is, right? In this case, if the exponent is larger, it has to be larger. Whichever exponent is larger, just make note of that. Yes, done. Now let's try to see the conversion. Yeah, so essentially IEEE 754 is used for storing large floating point numbers and all that we have seen. Yeah, fine. So now let's see the conversion. Let's say you are given a number like this: 42.6875. Okay, first of all, make that number in binary. That is the first step. Make that number in binary. Now binary, you very well know it. 42 is 10101. 0.6875, just multiplied by 2 progressively and get that binary representation. Now after this, we represented that into plus or minus 1 point f into 2 power something, right? There's a mistake here. That 10 should be 2. Okay, this 10 should be 2.
So we represented that, right? So that is called normalization. So normalizing this would be what? I have to shift this dot to 1 point something. So I have to shift that to 5 places to the left. In that case, I'll put into 2 power 5. 5 places to the left means into 2 power 5. So in this case, it'll be 1 point. Everything after that into 2 power 5. Getting this? So when I get this to this version, I can easily say, right? First of all, it's a positive number. Sign bit will be 0. Done. Right? Now I will see the significant. What is the significant? 0 1 0 1 0 1 0 1 1. How many bits is it having? It is having 9 bits. Okay, but I know that significant contains 23 bits, right? So I have to pad zeros to the right of it. I have to pad zeros to the right of it. In this case, I'll pad how many zeros? 23 minus 9 zeros. Yes. So what will be the exponent now? Exponent here is 5, right? So in that case, what is the bit system I'm using? Single precision system. In a single precision system, an exponent contains 8 bits. So n is equal to 8. So 2 power 7 minus 1 minus 1. So 127 I'll add. Okay, done. So 127 if I add, then it will be 132. I'll represent 132 in binary. That's it. Okay, so that will be my exponent. Okay, so this will contain beautifully 8 bits. This will contain 23 bits, 1 bit, total 32 bits. That is the example. Okay, so similarly, one more example is given here. 42.586, same thing. Binary conversion, binary conversion. Put them to the left and make it normalized form, and then put sign bit 0 here. Exponential is just whatever was the exponent plus the bias 127 in this case, single precision system. I'll put that in the exponent field with 8 bits, and the remaining bits are going to be the significant bits. And significant bits in this case is 0 1 0 1 followed by so many things. I'll pad zeros to then to make it 23 bits. Okay, that will be the significant part. So if it's double precision system, what will I do? Same process, same process. So how will that happen? Just the configuration will be different. Sign bit obviously 1 bit only. Exponential here would be 11, right? Significant would be 52, 52. So 1 11 52. There 1 8 23. Here 1 11 52. Okay, bias will be the same thing. 2 power n minus 1 minus 1. In this case, n is the number of bits for the exponential field, that is 2 power 11 minus 1 minus 1. So 2 power 10 minus 1, which is 1023. Okay, so 1023 would be there. And you'll do the same thing. Sign bit, put it directly, put it into nice binary form, normalize it further, find significant in binary form, pad zeros to the end to make it 52 bits, and exponential, add bias to it, make it binary, put it in the exponential field so that it becomes 11 bits. After all, that's it. You got IEEE fields. Okay, and if you want, you can see half precision and quarter precision also. I have given that, but that is not there for you. So that is all that is there. And that brings us to the end of COA course. Thank you so much. Is it all clear? Can I have a reaction from all your side? A reaction, please. Thank you. Yeah. Okay. Very good. To just give you a model, I have few previous year papers. I'll just quickly see, tell you what is there. I don't think I have the time to solve them. Okay. Not this, not this.
Mm.
This is my senior's COA paper. Okay, just
நல்லா
you can
அனுப்பவே
see.
இல்லை குரூப்ல.
Understand. So
ஓகே.
I'm not sure if you have booth algorithm. We had it. Booth algorithm. Partial. You have CSA also, no? I think these are all come after this, or you don't have it at all. Carry save adders and all. Do you have it? I don't think so. You learned. You didn't even learn it in digital design, I suppose. Yeah. And this 3-bit number system for sign, magnitude, ones complement, two's complement, we very well learned it. And the performance type questions and all, we didn't know how they'll ask. This Varma's paper, I believe, two processes A and B have clock frequencies of this and this. Suppose A can execute an instruction with an average of 3 steps per 3 steps, and B can execute with an average of 5 steps. For the execution of the same, which processor is faster, and justify why. How will you do this? They've given you the clock speed, and they've also given you the number of steps it takes. Which processor is faster? Any guesses from your side? Guesses. By the way, even these formulas, I think I still have the ChatGPT link for this if I remember. I'll check if I have it. I just put out all the formulas of performance, everything in one ChatGPT page. I think it should be there in my OneNote page. I'll see if I can export this and I'll send you. Okay, that is there. And about the paper in general, I would kindly advise you guys to go through the previous year papers. It's very important, very very important. There are chances that questions could come up from that region. We know about our professors, so make sure you do your previous year paper really well. Okay, I mean, just go through the PPTs once, but don't leave. At least have an idea of what the previous year papers are, so that you will know, okay, fine, I should present my paper like this, I should present my paper like this அப்படினு you will get an idea. Yeah, all right. So hey, எவனுமே கெஸ் பண்ணலையா? Very simple ra. Time is what? The number of cycles by clock frequency. In this case, it is taking an instruction is taking 3 steps. One step is executed in 1 cycle, so 3 cycles by clock frequency. So one will take 3 by 700 megahertz, the other will take 5 by 900 megahertz. Which is greater? Whichever is lesser is more faster. Okay, so in that case, I think which is smaller. Just do the math. That's it. Okay, whichever lesser time, that is faster. Okay, you can do that, and you should explain these processor things and all that. Okay, and mapping and all, you have good questions, please do that. I think you should have done that in your 3rd unit and all. Okay, I suppose pipelining question, very nice important question, right? All identifying these hazards, read after write, right after read, right after write, and all these hazards, right? I think pipelining lesson should have covered it properly, right? And what these hazards do, number of cycles if the process clock time is this much, just go through that once. Addressing modes, DMA controller for direct memory access, directly you get it from the memory input output without disturbing the processor too much. Yes, and all that. 5 stages and all that, if you want, you can see. I think it's the same thing. Just go through this. I don't think this slide, I didn't revise the pipelining slide, so I'm not sure. If it was this, just go through these pipelining formulas as well. Okay, and that brings us to the end of this. All the very best, guys. Do well. Bye bye. Tell me how it goes.
நான் ஒரு டவுட்டு. ஹலோ,